Hey Matrix, welcome back to the next video in the chemistry playlist where we're going over the November 2020 past paper. Today we'll be covering question 5, the rate of reaction question. If you don't have the paper, then please pause the video. You'll find a link in the description below where you can download the paper and the memo, and once you have the paper then we can continue with the question. Okay, let's get started with question 5. So question 5 is looking at the investigation of the rate of reaction of CaCO3 in different forms. So you can see we've got the balanced equation up here. They tell us that the mass of CaCO3 is the same in all three experiments, and they tell us that the hydrochloric acid is at a temperature of 40 degrees. Okay, then they give us the following table down here. We can see the volume of HCl stays the same and the concentration stays the same. But then here in state of division, we then have granules, lumps, and powder. So those are three different things there. Okay, so that will come into play somewhere. Okay, so question 5.1.1 says, for the investigation, write down the dependent variable. Okay, so reading up top here, the clue should be, it goes along and says, HCl is used to investigate on one of the factors that affects the rate of reaction. So what's being affected is my rate of reaction. Okay, so it's the dependent variable because it depends on how the reaction takes place or what happens in the reaction. Let's put it that way. So my dependent variable is going to be the rate of reaction, or reaction rate, whichever way you want to put it. Okay, now 5.1.2 is the independent variable. Okay, so this again doesn't depend on anything. So if we look in the table, yeah, the clue is the state of division. Okay, so we've got granules, lumps, and powder. Okay, it's not, these here don't depend on anything. Okay, but the rate of reaction depends on whether it's a granule, a lump, or a powder. Okay, so the independent variable will be state of division. Or we can say surface area. Okay, now 5.2 works off this graph down here. Okay, so we've got a graph which is talking about the volume of CO2, and we've got time at the bottom here. Okay, so it's talking about experiment A, and we're looking at how quickly CO2 gas is formed and caught in a syringe over a period of time. Okay, so one thing you should notice, from 0 to 20 we have a steep increase. Okay, the reaction's just started. From 20 to 40 there's a decrease in the rate at which volume is formed. From 40 to 60 it's decreasing even more, so there's a longer time period compared to the amount of gas that's formed. And then from 60 to 120 we have a constant volume, which means the end of the reaction or equilibrium has formed. Okay, so 5.2 says what can be deduced from the graph regarding the rate of reaction during the time intervals. So talking about 20 seconds to 40 seconds. So from 20 seconds over here to 40 seconds, we can see the rate at which the volume of CO2 is starting to decrease, okay, in that time period. Therefore, we have a decrease in rate of reaction. Okay, so from 20 seconds to 40 seconds, we have a decrease in rate of reaction. Okay, now from 5.2.2 it says 60 seconds to 120 seconds. Okay, so here we can see that the volume stays constant. So if the volume staying constant and not changing, there's no change in rate of reaction, so my rate of reaction is then 0. Okay, so rate of reaction, I'm just going to abbreviate it like that, is equal to 0 for 60 seconds to 120 seconds. Okay, now 5.3 says calculate the average rate in centimeters cubed per second at which CO2 gas is produced in the experiment. Okay, now you should remember that the rate of your reaction is the change in volume over change in time. But now they said the average, okay, which means we have to take into account the entire time period for which the reaction took place. So from 60 onwards, it's constant volume, which means no rate of reaction. So the rate of reaction takes place between 0 and 60 seconds, and there's a change in volume of 0 to 500 centimeters cubed. So all we have to do is plug in that into our formula, and that's going to be 500 centimeters cubed minus my initial volume, which is 0, all over my final temperature was 60 seconds minus my initial time, which was 0 seconds, and you should end up, if you plug that into your calculator, with 8.33 centimeters cubed per second. Okay. Now, 5.4 says, how will the volume of CO2 produced in experiment B compare to that produced in experiment A? Choose greater than, smaller than, or equal to. So let's have a look between the differences of experiment A and B. So the volume is the same for HCl, the concentration is the same for HCl, plus they said that the mass of CaCO3 is the same throughout all the experiments. So the only difference is that A is granules and B is lumps. But is there any way to determine the difference between granules and lumps? Have they given us a size scale, for instance, or have they given us a weight scale to say that lumps weigh this much and granules weigh that much, for instance? So as you can see, they haven't given us anything. So we can't distinguish between lumps and granules. So we can treat them as the same thing. So therefore, the difference in the experiments isn't going to be anything. There's still going to be an equal amount of volume of gas that is produced for the two experiments. So you can say equal to, or you can say that the volume will be the same. Okay. Now 5.5 says a graph is now drawn for experiment C on the same set of axes. How will the gradient of the graph compare to the gradient of the graph of experiment A? Greater than, smaller than, or equal to. Okay, so first of all, notice that in experiment C, we're dealing with powder and not granules or lumps. Okay, so we're going to have to mention that somewhere. Also note that it says, use collision theory to fully explain your answer, and it's worth 4 marks. Okay, so 4 marks, 4 pointers. So let's work through this in a logical step. So the first thing we can state is that experiment C is in powder form, whereas A is granules. Okay, now because of this, C is in powder form, okay, so therefore we have a larger surface area. So thus C has larger surface area. Okay, now the third point, we have to talk about collision theory. So due to the larger surface area, okay, by the collision theory, there will be more effective collisions or more efficient collisions, depending on which way you want to word it. But the main point is there will be more frequent collisions. That's the word I'm looking for. So more frequent collisions. Okay, and if there's more frequent collisions that are taking place, there is a greater rate of reaction that is taking place. So therefore, number 4, you can state, therefore, greater rate of reaction. Okay, so it will be greater than that of A. Okay, now the last question, 5.6, is a calculation question. So it says, assume the mole gas volume at 40 degrees Celsius is 25.7 decimeters cubed per mole. Calculate the mass of CaCO3 used in the experiment. Okay, so everything that's given to us, we've been given the mole gas volume, that's over there. We've got 500 centimeters cubed that we got from the graph of CO2. We know that the conversion factor for 1 centimeter to centimeter cubed to decimeter cubed is given over here. And we know the mole ratio of CO2 to CaCO3 is 1:1. Okay, so the first thing I'm going to do is convert the volume to decimeters cubed. So we're going to have 500 centimeters cubed over 1 multiplied by 0.001 decimeter cubed all over 1 centimeter cubed. That and that will cancel out, which means my units will be decimeters cubed, and that shall give you a total of 0.5 decimeters cubed. Okay, now that I have that, I can use one of my formulas. So if you look on your formula sheet, you should find the following. N equals to V over Vm. Okay, we have the volume and we have the mole gas volume, so that's just going to be 0.5 decimeters cubed all over what's given up here, so that's 25.7 decimeters cubed per mole. Okay, so because it's a fraction in a fraction, the moles will go to the top, so my answer will be in moles because these will cancel out. Okay, now we know that N of CO2 equals to N of CaCO3. Okay, so therefore they'll have the same mole ratio, which means this is equivalent to 0.5 over 25.7 moles. Okay, you can put that in your calculator and work that out so long. I'm just going to keep it in a fraction for now. Then in order to calculate the mass, we know that N, okay, equals M over capital M. So we want little m, that's our mass, this is our molar mass. So N of CaCO3 times my mass will equal, my molar mass will equal to my mass. Okay, so we have this, that's the fraction up here, 0.5 over 25.7. Okay, you can check your periodic table, but your molar mass should be 100 for CaCO3, and that's going to give you your mass, and you should get an answer of 1.95 grams. Okay, and that's how we go about doing this question. Okay, if you found today's video helpful, then please leave a thumbs up on the video. It does help out a lot. If you have any queries regarding the question, please leave them in the comment section below and I'll get back to them as soon as possible. Please go check out the channel. While you're there, please subscribe to the channel. There are maths videos and physics videos as well. And thank you for watching.